So you see that when we have the directivity pattern, so the directivity pattern we can show as a function of alpha x in this example. Why? Because we use a linear aperture. But sometimes we say, okay, we want to see, suppose that we said that this is x, okay, this is x direction. And the source, if the source comes from a certain direction compared to x, so this is phi, okay? So this is phi. And suppose that this is y, the direction y, and z is perpendicular to this way. So suppose that we say that theta is 90 degrees, pi over 2. Okay, so this becomes 1. It becomes 1 for theta equals to pi over 2. So because why? Because in this example we have circular symmetry. And then we can measure what is the directivity or the dependence of the electric signal that is measured at the output of the aperture as a function of phi. Okay? So you see that we have different directionality as a function of phi. And then instead of something like that as a function of alpha x, we can see what is the magnitude as a function of phi. This is as a function of alpha x. But as a function, the magnitude as a function of phi. Okay? So it will not be a sinc function like this. This is a sinc function. It will, because of this is the cosine. Okay? Or I can put as a function of cosine phi. Also it's okay. But I would like to put it as a function of phi. So it will look like this. Okay? Because it will be of a sinc of x, what I showed before. Okay? So for certain directions, when alpha x, you see, is an integer product of lambda over L, so we have nulls. Nulls, it means that signal that comes from certain direction will be 0. It will generate 0 electrical signal, which means, you see, that we can separate signals that come from different directions based on the frequency. And then, instead of something like that, sometimes we have a polar plot, which is very useful. By the way, when alpha x equals to 0, so cosine phi equals to 0, so this is, what is this? Pi over 2. Okay, so it's not 0. And it makes sense, you see, because if the direction is pi over 2, it means that the signal comes from here. This generates the maximum response, electric response. Okay? So we can plot the directivity in polar plot something like this, with certain circles like this. Okay, it doesn't look great. Maybe I'll just put a single circle like this. So how do we plot this? So this is x direction, this is y direction, and then instead of something like that, we can plot it like this. What does it mean? That each point here, it means what is the response. This is the response, the strength of the response to a certain direction phi. Okay? So if you see that for, I need to do it like this. Okay? So for pi over 2, we get the maximum directivity, the maximum response. So this is the maximum response. When I move to a different direction, it's smaller. So it becomes smaller. So this is the response, and so on. So different directions, we have different responses. And usually, the distance from the origin to that point, it means what is the magnitude of the electrical signal that is received, that is measured in response to a signal that comes from a certain direction. But here we do it in dB. Also here we can change that to dB, decibels. Okay, it doesn't have to be with linear. But we can change that in dB, but here it's definitely in dB. So this distance in dB. And usually we don't show, we need to limit the range of dB because we cannot measure something that is 0 in dB. It will go to minus infinity. So we can limit the range of dB that we want to show on this plot. And this is very common to show directionality pattern. Okay, that's why it's not important what is the directionality, but we need to know the relative directionality relative to a certain direction. So that's why we can normalize. You see, we can normalize the directivity pattern by its maximum value because it's not important. We can always change the strength of the electrical signal. What we're interested is to see the differences in responses to different directions. So in our case, we have sinc function of alpha x, and if we measure, because it's a linear aperture that is with circular symmetry, so we can put theta equals to pi over 2, and then it's a sinc function of cosinus phi, multiplied with L and lambda. So this is the normalized directionality, directivity pattern of this linear aperture without designing anything, okay? We didn't change. We just want to know what is its response. This simple case. Yes? What do you think? If I have the directivity pattern, and it's Fourier transform, but I need to know, okay, so it's three-dimensional Fourier transform of a certain aperture. So if I take the inverse three-dimensional Fourier transform, I will get the aperture function, okay? So I know what is the aperture, okay? And these are polar plots of directivity pattern for this simple aperture. So you see, it depends on the frequency. So actually it depends, we saw that it depends on L over lambda. So if the frequency is low, which means that lambda is large, you get something like that. Why? Because for low frequencies, the range of alpha x, you see, the range of alpha x, this can be between 1 over lambda to minus 1 over lambda. This is the range that is possible. So maybe the range is over here. So the range over here, with the polar plot, we will get this. And actually it makes sense. It makes sense. Why? Because if we have low frequency of the source, low frequencies, it means that the phase differences are very small. So if a source comes from another direction, the phase differences are very small. It accumulates. So the differences will also be related to this range of alpha x, to this range, because it's 1 over lambda, and this should be between -1 and 1. If lambda is small, so the range of alpha x can become with larger differences. So we have, when we increase the frequency, and we further increase the frequency, you see that the main beam, so it's the beam width become more narrow when we increase the frequency. These are called side lobes. Side lobes, it means when signal comes from a direction which is not within the main lobe, what is maximum strength? So these are side lobes. The main lobe, it means that when we take the signal that we intend to get maximum response to a certain direction. But we don't know exactly the direction. The direction can be here or here or here. So we have certain beam width around the nominal direction. And still, so this beam width, the beam, like we want to measure a signal that comes from a certain direction with a certain beam width. So if the frequency is high, the beam width becomes more and more narrow. This is the response of even such a simple aperture. Okay, so these are also some conventional terms. We call a source that comes from phi equals to pi over 2 or 3 pi over 2. So a source that comes from this direction or this direction, actually with all the circular symmetry. It's called broadside source. And if the source comes from this direction, phi equals to 0 or pi, okay, so we call it end fire. So for this kind of aperture. If the aperture is more complicated, so sometimes it's more difficult to define what is the broadside or what is the end fire. But for this linear filter, a linear array, so a linear array, and in this case it's even a uniform linear array. But for linear arrays, or linear aperture, it's very easy to define the broadside direction and end fire direction. So if you read about it, so you know what does it mean, broadside direction and end fire direction. After we understand what are a continuous aperture, we can talk about discrete sensor arrays. So discrete sensor arrays, actually they are combination in general of continuous aperture. So combination, okay? So when I talk that, suppose that my source doesn't come from the broadside direction, but it comes from a certain angle. And I want that the maximum response will be towards a different direction. Instead of 90 degrees, 45 degrees. I have a few options. One option is mechanical. Mechanical, it means that I take the aperture, I rotate the aperture towards a certain direction. But rotation also with antenna, many times they do that. But rotation takes energy and takes time. But instead I want to do digital rotation, okay? So it's called steering. So I want to direct the directivity pattern such that it will not be maximum for pi over 2 for 90 degrees, but for 45 degrees. So I want to steer it. Here you can see it very easily. So I want to steer that the response will be, instead of something like that, it will be something like that, to 45 degrees. How do I do that? Okay. So one possibility is to change the aperture function. What does it mean to change the aperture function? I want to change, I will add in the aperture function phase response. So it will not be like that. It will be complex, of course. It's a complex. So it will be a complex number for each frequency. And for each point along the aperture, I will put here the correct phase such that the signal that comes from this will be accumulated. How do I do that? Okay. Think about plane wave that comes from certain direction, from 45 degrees. So it comes to this point early. Then it comes to another point. Then it comes to another point, and so on. So if I put a phase in each point along the aperture such that it compensates the phase differences of the propagating wave, so it actually compensates for these phase differences. So a signal that comes, propagating wave, that comes from this direction will be accumulated, and then I will have the maximum response to that direction. This is called steering. But if I have an aperture like that, how do I change the phase, the response in each point along the aperture? This is quite difficult. But in practice, so what do? We don't use continuous aperture. We use discrete aperture. So instead of something like that, we take a few points like this, discrete aperture. It doesn't have to be with the same distance, but I take some points. And for each point, I measure the signal, the electrical signal, so it's a point aperture. And for each point, I will take the signal that is received here. Now I can measure all these signals. I will multiply each signal with whatever I want, because I can do it on a computer. I can multiply this with a certain complex number that includes magnitude and phase. I can multiply this. So I will multiply this. Let's say this is sensor number 1, 2, 3, and so on until M. Here I will multiply it with W1, F, because it depends on the frequency. Multiply it with W2, F, and so on until this. I will multiply it with WMF, and then I will take summation of everything. Summation, and do like that. So instead of continuous aperture, I use discrete aperture, and I put here, using a computer or processing, I will add that and get the electrical signal. Okay? So actually the design of these weights, these are called beamforming. Why? Because with beamforming, I can design a desired directivity pattern. the simplest way is just steering to move it to a different, so the maximum is in different direction. But maybe I can change also the directivity pattern such that the side lobes maybe are lower. Or maybe, just like we saw before, that the width, the beam width, the main beam width depends on the frequency. Maybe I want to change it so it's not independent of the frequency. So we have different ways to design the directivity pattern. Okay, so discrete is just like sampling, sampling the continuous aperture, and actually each point doesn't have to be a point sensor. It can be also continuous. It doesn't really matter. So what do we do here? So the aperture function, actually what it will be, like what I showed here. So it's the aperture function of each sensor, each discrete sensor. We multiply it with a certain weight. This is part of the design. This enables us by an algorithm to design these weights, and then we take the summation. So in this example, we have n sensor, n discrete sensors, and we put them from minus n minus 1 divided by 2 to n minus 1 divided by 2. So we assume that n here is an odd number, but it doesn't have to be. It's just a summation. It's a superposition, like this. So the aperture function of this summation will be summation of the aperture function of each individual one, when it's in a certain direction, in a certain point. Okay, we change it to a certain point. So if, and also the directivity pattern will be the summation of the directivity pattern of each one multiplied with the weight, and also we have here this exponent. Why? Because of the position of each sensor, it's in a different position, so this shift of the sensor accounts after the Fourier transform to a phase shift because of where it is placed. Okay? So let's see what is the response of something like that. So suppose, just for simplicity, that we use sensors that their aperture functions are delta function, okay? What is the sensor? What is the aperture function of a sensor? It means what is the response of the sensor to a propagating waves that hits that sensor. So if I tell you that is a delta function, it means that the aperture, it doesn't depend on the frequency. It doesn't depend on the frequency, you see? And also, it doesn't depend on the direction where the signal, the propagating wave comes from. So it's just a delta function. So if I put here, this we call omnidirectional sensors. So this is like ideal omnidirectional sensors because it doesn't, the reaction of the response, it doesn't depend on the direction, and it's also ideal, it doesn't depend on the frequency. So we get the total, or the total aperture function of this discrete, discrete sensors like this. And the directivity pattern will be summation of the weight with, instead of delta, the Fourier transform. So it's an exponent like this. So if we put, you see, I make very simplified ideal cases of design, okay? Even here, we want to understand what do we have. So suppose that we use uniform linear array. Uniform linear array. What does it mean? That the distances between the sensors here, the distances are the same. So let's assume that the distance between two sensors is d, is constant, is d. So instead of the distance here, we put nd. So we get this form of directionality. And suppose that we want to know only the horizontal directivity pattern, which means that theta is pi over 2. Because in this case, it's very simple. We have circular symmetry. So we have this expression. And not only that, suppose that we put the same weight to all the sensors. The same weight, 1 over n. Same weight to all the weights are constant. Just to see what will be the directivity pattern. So if we take summation, so when the response will be maximum to a propagating wave that comes from this direction, from 90 degrees, okay? Because here, it will come with the same phase. But if it comes from another direction, it will be different, okay? So we want that even if we put here the same weight, to see what is the effect of the number of sensors and what is the effect of the size of the sensor array, what is the effect of the frequency, okay, and so on. So we will check what is the effect of n, the d, the distances between the sensors, the frequency, and of course, and afterwards, what is the effect of the weights. So the effect of the weight, we will talk about it separately because it's beamforming, is to design the directivity. But suppose that the weights are constant, we can see what is the effect of this, n, d, and f. So we can see that if you take summation, the summation like this, okay? So sum, where is this? So you know that summation from n equals to 0 to n minus 1 of A0 q to the power of n. So we have this formula, okay? So we can write it as A0 y minus q to the power of n divided by 1 minus q. Okay? So it's very simple. So if we use this, so we have n terms. So we have this summation, and we have q to the power of n, something like that. So if we take this summation for Wn, f equals to 1 over n. So it's constant. So what do we get? We get Dirichlet function. So we get this. This is the Dirichlet function or periodic sinc function. So it looks like that. How does it look? Let's see how it looks when we change the number of elements, n, and L and F are fixed. So if we change the number of elements, n, what do we want to see? So the directivity pattern as a function of phi. Okay? So it looks like this. So it depends if I'm inside here. Okay, so it depends on the range. It doesn't have to be like this. I will talk about it. Okay, so this is a periodic. So we want to see what is the level of the side lobes and also the beam width. What is the width of the main beam? So if we change n in this previous function, in this function, if we change n, what do you see? If we increase n or make n larger, but we keep the other, we keep D, we keep L and F fixed. So D multiplied with n is fixed. So if we increase n, but we don't change L, so it means that we add more samples along the continuous aperture. What will happen? You see that the beam width remains the same for a certain frequency, of course. Certain frequency, it remains the same. But when we increase n, the side lobes become lower. So it becomes lower until if we increase n to infinity, what will happen? Okay, like the sink. Okay, minus 13 dB. Okay, it's just like continuous aperture. So it will converge to a sink. What happens if we change D? If we change D, but we keep n fixed, 5 sensors, and we change D. So if we increase D, actually the size of the array increases. So if the size of the array increases, the main beam width decreases. Okay? So we have more narrow. When we increase the size of the array, the width. So we have more directionality. The directivity pattern, the main beam, becomes more narrow. So we have more directionality for the same frequency. What happens if we change the frequency? So if we change the frequency, you see this is the frequency, and this is the angle, phi. So if we change the frequency between 400 hertz and 3 kilohertz, and n, the number of sensors is fixed, and D is fixed, so the size and the number of sensors is constant, and the size of the array is constant, we see that for low frequencies, we have wide main beam, that we have lower directionality, because we have phase differences which are small for low frequencies. But when we increase the frequency, we have more directionality. Okay? Now, if we further increase the frequency, if the frequency goes up and up and up, what will happen? We'll have aliasing. It's just like with time samples. If we have signal and we sample the signal with a certain time interval. So if the frequency is high, it imitates, we cannot distinguish between sampling of a certain signal and another signal with higher frequency. So we cannot distinguish between them, which means that in order to not have aliasing, which means that we design the maximum response to a certain direction, okay? Suppose here that we design it to a certain direction. This is the maximum. And all these are side lobes. But it depends on the frequency. So maybe for higher frequencies, we get high response also to another frequency, to another direction. So we cannot distinguish between the signal that comes from this direction and a signal that comes from another direction, because with high frequency we can have different directions with the maximum response. So if we want to avoid aliasing, we need that when we sample the aperture, the sampling frequency, which is 1 over d. D is the distance between sensors. It will be larger than the maximum frequency change within this aperture, which is 1 over lambda, lambda minimum, the minimum wavelength of the signal. Which means that d, the distance between sensors for uniform linear array, should be smaller than half of the wavelength, half of the minimum wavelength of the signal. And we know this is spatial sampling theorem, just like it's the Nyquist frequency. So it's the same. It's the same. Let's see the response. So here, you see in this plot, d is lambda min over 2. So here we see that in this case, the maximum response is for 90 degrees. So we still have the response to 270 degrees because of the circular symmetry. It's a uniform linear array. Uniform linear array. And, but the response in this direction, for example, is smaller. The response in any other direction between 0 and 180 is much smaller than the response to 90 degrees. But here, lambda equals to the wavelength, the lambda mean. So for this frequency, if we increase the frequency such that the wavelength equals to the distance between the sensors, we see a large response also to a signal that comes from 0 degrees. And this is undesired. It means that if we have two sources, one that comes from 90 degrees and one from 0 degrees, with that frequency or that wavelength, we cannot distinguish. We don't know what is the direction of the source. Okay, so I talked about radar. Radar. So I transmit a signal, electromagnetic wave. I received it back, and based on the phase differences, I know what is the direction that it comes from. So if the frequency is such that the wavelength is such that this is satisfied, okay, such that the distances between the sensors is smaller than the minimum wavelength, then based on the phase differences between the sensors, I know exactly the direction where it comes from. But if the frequency, you see, is higher, high frequency, such that lambda mean, the smaller wavelength, equals to the distances between the sensors, I think that it comes from 90 degrees, but actually maybe it comes from 0 degrees. And actually if I go with higher frequency, maybe I have another lobe. I have a side lobe that is strong from another direction. So I will not be able to know what is the exact direction of the target. Okay? That's why it's important to know, or it is important to satisfy that D, the distance between sensors, will be small enough. So the sampling frequency along the continuous aperture is dense enough. Okay? The last thing I want to discuss is the array gain and directivity factor. Okay, so maybe I don't, 6 o'clock. Okay, okay, so I will talk about array gain. So it's just these terms I want to talk about. What is the array gain and directivity factor? Okay, array gain, it means what is the improvement in signal to noise ratio of the array compared to a single sensor. So you see, if I use here one sensor, but instead of using one sensor, I use n sensor array, I want to obtain something. So I ask myself, what is the improvement in signal to noise ratio? So the improvement in signal to noise ratio, it's called array gain. You see? This is the array gain. So this is the gain in signal of the power of the desired signal. This is the average gain of the noise, the background noise. So this ratio will be the array gain, the improvement in signal to noise ratio at the output of the array compared to a single sensor. So, of course, this array gain, it depends on many things. It depends on the number of sensors. It depends on the configuration. It depends where the desired source comes from, right? Because if this desired source comes from this direction or from another direction, it will change the array gain. But also, it depends on the average gain of the noise sources. So it depends what type of noise I have. What are the direction of the noise sources? What type of noise? So in case the noise source is diffuse noise. What is diffuse noise? Noise that comes with the same power from all directions. So this is like theoretical type of noise. So we have different noise fields. The most important noise fields are spatially white noise. It means like thermal noise, that the noise in each sensor is independent of the noise in other sensors. This is spatially white. So if we put here, what is the array gain for spatially white noise, so for thermal noise, we will call this array gain, we will call it white noise gain, which means that this is the array gain when the noise is spatially white, thermal noise. If we put here noise that is diffuse, that it comes from all directions with the same power, we will call this array gain directivity or directivity factor, the same. And this is very interesting because directivity is very important. It shows what is the improvement in signal to noise ratio under conditions that noise comes from all directions. Sometimes there is many sources that come from different directions, like in a conference. Many people speak at the same time and so on. So there are many noise sources from different directions. And we want to know what is the improvement in signal to noise ratio of the desired signal compared to the background noise in these conditions. So we call it directivity factor. Directivity factor is very important measure that we are interested. We are interested to improve the directivity factor. But we also want to improve the white noise gain. Why? Because the sensors are not ideal. We always, any sensor that you take for camera, for antenna, for anything, they have thermal noise. Microphones, they have thermal noise. So we want to know what is the improvement of the signal to noise ratio when we have thermal noise. So suppose that I tell you the white noise gain is minus 50 dB. What does it mean? What do you think? What does it mean? Minus 50 dB white noise gain. Yeah. So it means that the thermal noise in one sensor will be multiplied, will be stronger, but by 50 dB at the output of the array, which means that you need to use expensive, very expensive microphones with low thermal noise. If I tell you that the white noise gain is minus 10 dB, it means that the thermal noise will be amplified by 10 dB at the output. Maybe it's okay. Maybe the thermal noise is still low. Okay? So thermal noise at the microphones, you will listen, if the array gain is very low, like minus 50 dB, it means that it will be amplified at the output by 50 dB. And then we need to be very careful not to design directivity pattern with very low white noise gain. And we will see when we study this course that there is a trade-off. The more that we want to increase the directivity factor, what is the directivity factor? I just said, so you don't see it. What is directivity factor? Exactly, improvement of the signal to noise ratio when we have diffuse noise. So we want to improve the directivity factor. Why? Because then we have more directivity. We can suppress noise, background noise that comes from all other directions. Because maybe we don't know the direction of the noise sources. We want to suppress them, so we suppress all the other directions. We want to design a sensor array with our large directivity factor. But then what will happen? We will see that the white noise gain will become lower. So we need to use more expensive sensors with low thermal noise in order to allow. Or if we use certain sensors with a certain level of thermal noise, we need to limit the white noise gain. Okay? Any questions? Okay, so we'll stop here. We will continue here tomorrow morning, 9 o'clock.